As the PID block is customarily used in the process industries, the derivative mode is based on the PV. Some control systems provide the option of basing the derivative on either the PV or the control error E, but even in these, the default is usually derivative based on the PV. This video explores these issues. In the previous video, the derivative mode was the result of projecting the PV one derivative time into the future. An alternative is to project the control error E one derivative time into the future. At a point in time, two items of information are available for the control error E. Number one, its current value. Number two, its rate of change, or DEDT. The current rate of change in the control error E can be used to predict future values for the control error E. The projected control error E hat at one derivative time in the future is E plus T sub D DEDT. The value of DEDT reflects the rate of change of the set point as well as the rate of change of the PV. Issues arise for changes in the set point. Except for abnormal events such as equipment malfunctions, abrupt changes in the PV do not occur in process applications. But abrupt changes in the set point occur routinely. In previous videos, the set point for the hot air temperature was changed from 210 to 220 degrees Celsius. This is an abrupt change of 10 degrees Celsius. The control error E also abruptly changes by 10 degrees Celsius. This has consequences on DEDT. A subsequent video examines the numerical issues associated with computing dPV/dt in a process environment. When derivative is based on E, this must also address abrupt changes in the set point. For the moment, all of this will be deferred to the subsequent video. To obtain the PID control equation, start with the PI equation written in its customary form, but with E hat instead of E in the proportional term. Control output M equals K sub C open bracket E hat plus 1 over T sub I integral of E dt close bracket. Replace E hat by the relationship just derived, specifically E plus T sub D dEdt. M equals K sub C open bracket E plus T sub D dEdt plus 1 over T sub I integral of E dt close bracket. Finally, rearrange so that the terms are in the order suggested by PID. M equals K sub C open bracket E plus 1 over T sub I integral of E dt plus T sub D dEdt. The proportional term is E. The reset term is integral of E. The derivative term is dEdt. When based on E, the sign on the derivative term is positive regardless of the controller action. The hot air furnace will be used to illustrate PID control with derivative based on PV and PID control with derivative based on E. Open the point window for the hot air temperature controller and display the tuning parameters. The controller gain is 1% to percent. The reset time is 0.8 minutes. To obtain PID control, change the derivative time to 0.2 minutes. The derivative is based on the PV, as will be confirmed shortly. Switch the controller to auto. Change the set point to 220 degrees Celsius. The response exhibits an overshoot of about 2 degrees C and an oscillation that decays rapidly. No second peak can be detected. Switch the controller to manual. Then place the simulator in hold. Open the configuration window and select the Algorithm tab. The current selection for derivative mode options is based on process variable, confirming that the derivative was based on the PV for the previous response. Expand the drop-down list and select based on control error. Save the change. Return the simulator to run. Switch the controller to auto. Change the set point to 210 degrees Celsius. The overshoot's about 1 degree Celsius when derivative is based on E, as compared to about 2 degrees Celsius when derivative is based on the PV. Place the simulator and hold. Examine the controller output, the yellow pin. With derivative based on E, the abrupt set point change causes the spike or pulse that is exhibited in the controller output. When derivative is based on PV, there is no such pulse. The pulse raises two issues. First, only rapidly responding final control elements will propagate the spike or pulse to the process. Second, concerns regarding wear and tear arise for final control elements of a mechanical nature, such as control valves. In practice, the difference in performance is too small to offset the consequences of the spike or pulse. The difference in behavior only applies to changes in the set point. Performance for disturbances such as the fresh airflow is exactly the same. Even though derivative is generally based on the PV, writing the control equation with derivative based on E is common practice. Replacing E by PV in the derivative is viewed as a necessary modification to obtain a practical control equation. By this logic, one should feel free to write whichever form is most convenient. The next video discusses how the calculations for a PID block are performed. Some find the difference equations to be more informative than the differential equations we have been using.